Ever wondered how a debugger works? Okay, let's have a look. In this video, I want to develop a very simple debugger for the FreeBSD operating system. For that, just going to create a directory that I'm going to call debugger. And the first thing I'm going to do is I'm going to create a small test program. Include stdio, include stdlib, and let's define here a function, factorial of n, and if n1 is n, return 1. Otherwise, I'm going to return n times the factorial of n minus 1. Okay, now int main, int number of arguments, the parameters, the arguments is in the argv. Now I'm going to say that if argc less than 1, less than 2, let's say that the default case is going to be this one. Otherwise, let's put here int x equals 0. It's good to initialize this. And let's say that x equals to the factorial of why not, number 2. And otherwise, x is the factorial of a to I of the argument. Let's call the first argument and printf factorial of this is equal to that one. Factorial of arg, well, we need a parameter, int parameter, let's say equals to 2. Okay. Parameter equals to 2. And here we're going to see that the parameter is going to be the a to I of argv of 1. And now we can put the p and the x. Return 0. Looking good. Let's start a terminal. Before that, let's create a small makefile. Where when we compile all, we're going to get the cc-o test on test.c. And we're going to get a clean that we're going to remove test.o, test.core, if we have a core dump. So make, what about test? Factorial of 2 is 2, yes. Factorial of 4 is 24. It's looking good. We might want to add debugging symbols here. Make. On the test we have, where is it? Yeah, here is our function factorial. It's all looking good. Let's exit. Now we're going to start our debugger .c. And I'm going to start again with the same thing, include stdio, stdlib, int main, int argc, char argv. Let's put also the environmental variables, the environment variables. Return 0. And let's get this file compiled also. Here I can select to optimize and get the debugger with debugger.c. And here we can say test debugger. Here, yes, looks good. Make debugger compiling well. Okay, starting to look good. So the first thing that I would like to do is that I would like to start a program by itself. And for that, we can do the exec method. Let's try to think a little bit. For this case, I'm going to do an exec. I need to configure VI in distant computer. Exec VE, exec VE. I think it's this one. Let's just confirm. Exec VE. The exec VE. Yes, it takes the environmental, the environmental vector. The environment variables. So it's going to be argv1, the first parameter. I think, yes, the path, the cons to argv, and for the env. So it's going to be the arg, because we need to skip the program, the program name, so we need to give it like this. And here the envp, or yeah, they call it envp. Let's just call it the same way. Okay, first point of trouble. Probably I'm missing some defines. I need the uni std. Let's get this in. Oops, too many keys. PUT. So on the debugger, I'm going to call the test. Okay, and with number 4, it's 24. With number 7, okay. Number 6, 720 is looking good. Now, one of the things, so in order to get the debugger up and running, the main function that we need is the so-called the ptrace, the process trace. We have a really nice manual page here. And if we read this, we're going to see that, okay, some things here, syscall fork, ptrace me. This request is used by the traced process. It declares that we're expressed to be traced by the parent. That's exactly what we want to do. So the first thing is that we're going to do here is we're going to call a fork. We're going to fork the process. And for that, we're going to see that we will have one process that is going to be the 0. Return event to the child and the process ID to the parent. So 0 to the child. So here 0 fork. Else, okay, we don't need this actually because we can just return. Okay, 1, 2, 3, 4, 1, 2, 3, 4. I need to configure Vim properly. Return, or let's call it exit 0. Let's just, for the time being, just write printf child process. Knowing how to type also helps. And here, parent. And what should we see? We should see a child and a parent being executed, as you can see here. The child is the one that where we're going to run the exec VE. So we don't want to print a child. And we want to trace me, right? So man ptrace, trace me, trace me, pt traced me. Okay, so it says that the process expects to be traced by the parent. So what we need to do here is ptrace. Ptrace, come on, you can do it. And let's go here. So we need both of these imports. Let's just copy this. Starting to look good. Ptrace and request. So let's just copy this for the time being, just that we know what we're expecting. And the trace me. So this is going to be the parameter, the trace me. So the request, pt trace me. The PID, what can we use for a PID here? We can use the, let me see. So it says, is used by the process. All the other arguments are ignored. Okay, so we don't really need this one. This is ignored. This is ignored. This is ignored. We should be good lads and we should get the return value. Let's try to see return. I only write the return because maybe R is capitalized. Okay, what else do we have here? Okay, this is way too much description for me. Okay, return. Most requests 0, on error -1. So let's write a small function here. Let's call it the error function, void error. And let's give it a message. And this is going to get a printf. Let's actually use the p-error function. The p-error, print the error. This is the first page. I think in the third page. Yes, in the third page we have the standardized stdio. We have it. And yes, so it function finds the error message corresponding to error number. It's going to be useful. So p-error on the message. And then let's just guarantee that we have an exit, a clean exit. Actually, let's indicate an error like this. So, and for the ptrace, let's go again. pt trace me. It actually said return and return values, it's a negative. So if this is less than 0, error ptrace me. Okay, then we exit there. Let's compile. It's actually going well. So now we have executed. Let's try to take this one out. Okay, it says here the factorial. Let's decrease the size a little bit so you can see better. So factorial is that much. Now we bring the trace and we recompile, and we don't see anything. The reason we don't see anything is that on ptrace me, this process is stopped. So let's see if we can see that. ptrace me. So it does start a new process. All the when the process is it will stop before executing the first. So it will stop the process. So from the parent, we need to tell this the process that it should execute. So what we need to do here is we need to tell it to continue. Let's try to do from here, ptrace. There should be a continuation. Continue, maybe. Yep, pt continue to continuous execution. So pt continue. The first parameter, I'm always forgetting this, it's the PID. We get the PID from, well, we don't get it from here. Then let's grab the PID. PID. So 0, PID is going to be equal to that one. PID. So here we grab the value of fork to a PID and then we compare it to 0. Actually, let's do this in a nicer way. So let's get this out here. Let's get it here. Here you can see it's a little bit better. Okay, continue. We need to give it the PID, and what else do we need to give? pt continue. We need a new value for the program counter, or to indicate that the queue is okay. So we need to have this one here to say continue where we left off, and the data argument address is the address specifying the place. So this is the data argument provides a signal. So this is the data. Provides a signal. 0, no signal is to be sent. So we don't want any signal for the time being. Make. Okay. Didn't go. The reason for that is probably because, let's try here, print f child. I'm guessing that I'm seeing first the parent and then the child, and this is not good. Parent. Yeah, I'm seeing the parent before the child. This is not good because we didn't execute the process and we're already telling it to continue. We cannot do that. So what we need to do is we need to wait for the process to start. For that, we need to call the wait function. Let's see. Man, wait. Okay, probably on page 3. Ooh. Wait. That was too much for me. Let's see, sig wait, p wait, no. This is way too much information. Ooh, okay, I'm just going to go the stupid way, and oh, it was manual page number 2. Okay, standard system C, standard C library. We didn't have the wait system call before. Now we need it. Wait with the int status. So we need a status. Int status. And now let's say wait for the status. Make. And now hopefully we should first see child and then see parent. Yes, we first see the child and then we see the parent. Although we didn't see the execution, which I'm not very happy about. What could this be? I'm just thinking a little bit. ptrace. With the PID. It should definitely, now it should definitely be executing the program. Or maybe, maybe I need to do again another wait. Yes, I needed to do another wait because then I exit this program. So first I need to wait the child to start. Then I need to tell it to continue and it should run to full execution. And then I need to, the parent needs to wait that the child is exiting. Okay, that looks a little bit better. So one of the things I would like to do is I would like to set a breakpoint on the program. So as you can see, we are already starting a new program which is being traced. So this is the beginning of our debugger, but we are not stopping anywhere. For that, what we're going to have to do is we're going to have to get an address to get the breakpoint. Let's just take the address would be, for example, at the factorial function would be this memory address. And let's pass this as an argument to the program. So let's modify this a little bit. So we're going to say here the int breakpoint address. I think it should be like this. Let me just think a little bit. No, it should actually be a pointer. In C, char pointer is the universal pointer, so we are fine. Then let's just put an exit. And why am I putting the exit here? Because if I recompile this now, the program is doing nothing. So I can try to think about grabbing the thing. So here, if we're grabbing on the first, I can take one parameter to get to pass in the address where I want to set the breakpoint. So let's shift this to the right by 1. Let's put it at 2. And let's say that the BP address is going to be the str string to long. String to long, how does this work? Str to long. Limits, stdlib and limits, that's what we need. We have this already or not? stdlib, yes, but limits we don't have. So the stdlib we had already, but the limits we didn't have. And now what we need is to get the argv1 0. Okay, now let's just protect this a little bit. So we need at least 3 parameters. If 3, I always like to write the things in the other direction, because if you say, for example, arg counter equals to 3, this will compile. This will not compile. Sorry, this will compile. Yeah, I'm saying everything wrong. Both of them will compile. And that is a problem, because this is an assignment. But if you write it 3 equals. Okay, so let's continue. I had a small interruption there. So ptrace requires a PID, which is of this type, PID-T. And we need this value here for our memory. What we're going to have is also a memory address, and this is the CADDR-T, which is the same as a char star mem address. We're going to do it like that, or mem ADDR, and we are good to go. We don't need anything else. So we need this one, the PID, and we definitely need the mem ADDR. And the same game as before. In this case, let me see. Yeah, we are in the ptrace, pt read I. The request reads traditional allowed machines conceptual in the current. If I'm not mistaken, there is something for this one here. Yes, exactly. In the return values, read I return the value read. Exactly, because there is nothing here in the interface that is going to give me the return value. And therefore, actually, I do have a data parameter that I forgot, but this data parameter is not documented to be a pointer to the return value. So actually, what we have here is something like, let's put it here, an int value that is going to be equal to this one. So how does ptrace report an error? Here we can see to this error number can be set to 0 before the call and checked afterwards. So let's set this variable to 0. And if we have something there, then we have an error, pt read I. Otherwise, we return the value. Okay, we should be able to compile. No. What happened? If error number okay, man error number, I'm probably missing, yeah, I'm missing an include for the error number. So we get it there. Let's compile. Oops, a little bit less errors. Memory address, ooh, is the I there. This is fat fingers. Fat fingers. Okay, looks good. But this function now is not being called. Now what we can see is, let's see if this function is working properly. So what I'm going to do is an object dump on the test. Okay, for sure I need to get the -t. The -t should be the disassembly of the program. Where is it? Yeah, -t, alias for disassemble all. Oops, that was too much, so we pipe it down to less. And we're going to search for the factorial function, which is located exactly at this address, and it starts with this value, 5548, etc. So let's try to read that value. And we know this is at the breakpoint address that we want to set. So let's try to read it. So parent, before continuing, let's try, let's write here original. Original value is read memory on my PID is going to be Where do I want to read it? I want to read it at my breakpoint address. And I think there are no more parameters. No, there are no more parameters. And now I just do a printf value at this is equal to let's say 0x. This cannot be a pointer, so 0x percentage 016 LLX. That should be fine. And BP address, and again I'm writing this all wrong here, comma and original value. Let's see what this does. Okay, it's complaining about something. It's not a long. Okay, then we reduce this a little bit. This should be 6 with a long x. Still doesn't like it. Then it's just an x. Sorry for that. Okay. Good. Okay, now we are reading some value, and let's see E5 8948 55. You remember little endian, big endian, so let's read this from right to left. So it's 55. Let's go here. 55. 4889 E5. So 48 here, 89 and E5. So we are sitting exactly in this function. And now what I would like to do is I would like to replace this 55 with CC, which is let's see actually if we have an int 3, I guess. Yep, a CC. It's an int 3, so it's a trap. I would like to replace this with CC. Let's try to do it. So let's define a trap value that we want to write back, and first let's compute it. So the trap is going to be equals to what? The trap has to be from the original. We need to end it with everything with zeros at the end. So tilde 0xff. So that should be fine, and then we add the CC. That should be good, and then we say, okay, we want to replace this with and 0x percentage 08x and with a trap. It's a tap. Nah, it's a trap. Okay, let's try it. Okay, we see that this 55 has been replaced with CC, exactly as I was wanting. Now we need to write this value back and let execution continue. So for that I'm going to write again another small function, that is, I'm going to call it, this doesn't need to return anything, write to the memory, and I'm going to require a PID. Let's be a little bit tidy. I like to give some spaces here. Is just a programming thing. Okay. You don't need to add the spaces if you don't want. So what we want to write, okay, where do we want to write? We want to write it to a memory address. And the next thing would be what we want to write, the value. Okay, beauty. Now, ptrace, pt write I, if there was the read, there should be the write. Yes, the data argument supplies the value to be written. What was the data? This is for the first time we're using the data argument. So it's pt write I. So we're going to say ptrace pt write I, on the PID at the memory address, and now the value. That should be it. Now, should compile, I guess. Yep. Now, let's be nice. If this is less than 0, we have an error. pt write I. Okay, that we would not even need for a function here, but it's written, it's done. Let's continue. So after computing the trap, so here I read the memory, I compute the trap, and I write back the memory. So write to the memory, and now I need the PID, the breakpoint address, and I write back the trap. Now the program should not run to its fullest because it's going to do a trap. Let's see. Yes. The difference is, let's try to show this. Before, when I ran it, it says factorial, and now the factorial is gone. Why is that? This is really as expected. The thing is, I'm doing a trap. So when I'm telling to continue, now the wait here, what is happening in this wait state is that the program is stopping because of the signal trap. So we need to catch the signal trap, and let's see. I think it was page 2, right? Wait, do we have something here? Yep, exactly. We have here the options, the stopped alias for okay, so we want to have a stopped bitwise OR. And what we have, there was some macros maybe used to test. Exactly. If stopped on the status. That's exactly what we want. So we have here the status. So if, not that one. If copy, no copy. Okay. W if stopped on the status. And do I have a signal? Not. If stop is true, if it is to the number of the signal that caused the stop. Okay. So we need a W stop sig. We need to know the reason. So if this is the, if we stopped and the W stop sig on the status, and what values could we have here? Do we have a description of the values we could have? Yeah, no, the signals, no. Let's see, user source. Is there a source again? So let's go there. User source, find signal.h, and I have sys. Okay, sys signal. Okay. Well, okay, we have lots of signals. We have, in this case, it would be the trace. Yeah, the trace, the trap trace. But there should be a signal for a sig trap. We need a sig trap. So let's put it on the other side. Sig trap. Is this the correct thing? With underscore? No, it is not. Trap equals this. What happened? That was not intended. And let's first just say printf here. We are here and we know that we received a trap. I can't, this just compiled the first time, awesome. Here, I'm here. Okay, so we are stopping at a trap. So what we need to do, we need to get, let's just say that we want to see, we want to continue from here. Okay, make, and let's run. Still nothing is printing out. Let's try now with 1. It is still not printing out anything. Because probably I still need to have a wait here at the end. Let's say here, nothing is printed, 1, nothing is printed. Okay, that was not expected. Let me just add another one just for the case. No, okay, and then it would be waiting for something that it should not be waiting. Okay. So let me think. So it would come here, would wait, continue. And it should exit. Okay. Finding it a little bit strange, but let's repeat this another time. Just okay. Also not happening. We have it here. Why are we not seeing the end result? If we have test 1, we have the factorial of 1 is 1. Okay. Yes, we are not seeing this because I'm telling it to continue, but the trap is still there. So we are still getting another trap. Let's try to see that this is the case. Printf. It's a trap. It's a trap. So let's try to continue. It's a trap. This should not happen because we have not removed the previous trap, so we are going to have to remove it. And the way that we do this is we need to single step. So we're going to need to write some things here. So, okay, we need to write, before we continue, we write not the trap, but we write the origin. We write it back and then we continue. And now let's see. And probably again what happened is that we are at the wrong, yes, we are at the wrong address in memory. Okay, so we need to set the registers. We need to read the registers and to set the registers most likely. Or let me see if it main ptrace. What is happening here? pt continue. pt continue. So the address specifying the place where execution is to be. Okay, the address. Let's try to give it the address. Instead of being 1, we try to say it's at the BP address. Now it's looking fine. So we did stop here. Print f here. We did stop here, and then okay, let's try to do this again. I was interrupted for a second time. So where was I? I have the, let me see, I need to run it again because I don't remember where I was. Okay, here. It's here, registers, write to the memory, original, continue, and done. Okay, a good next step would be to print out the registers. For that, I mean, we don't really need to do it, but just to make it a little bit more clear, I'm going to write a generic function called print registers. And for that, we're going to have a struct reg and a pointer to ptreg. And probably because of the instruction pointer, we're going to have minus. We're going to need this one. So let's start with a simple thing, print f. We can just say rax, and these registers, so let's put them like this, percentage 0, let's make them as if they were pointers, and going to print here, so the ptreg should have a structure which is the, I guess, the register rax, and here we can close. Let's see if this compiles. Format, it's a warning. Let's try to get rid of this warning. That's okay. Debugger, no format. This is not a very great idea to do, what I've just done, but turn off warnings from the compiler, but this is just a small demo. Debugger.c, and then we get the registers, and then here print the registers. What we need a pointer to the ptreg, and for now we get 0. Let's try again. rax is 03, that was not great. So let's say 0 with 16 numbers. It's a long hexadecimal value. I guess this would be going to be better. Yes, looks much better. Tab, which other registers can we use? Do we have the rbx? Probably yes. Percentage 0, 16 llx. And here ptreg register bx. Let's go for it again. Okay, we have already 2 registers. Since this is becoming a little bit boring to do this, let's just try to go here and take this construction and put it into a define. Define reg format, and it's going to be this one as a string. We don't need so many letters, and here we can just take this one, rfmt, and here the same thing. rfmt should still compile, should still run. Great. Well, we can go wild here on these things, so we could add another tab. Let's add the RCX register. Let's make it consistent here. rfmt with the ptreg register RCX. Okay, didn't save. Hello? Save. It would be great if you do it. Yep. There we go. We have 3 registers, and I'm just going to add a couple more. So RAX, what could we do? We could do the DI, the SI, and let's say the R8. So we take here RDI, SI, R8. Hopefully this still compiles. Something went wrong. Aha, this should not be there. We are getting there. R8, oops, 9. Since we are there, let's get the register 10, register 11. So we get here the 8, the 9. Please, oops, the 8 was done already. So this should be the 9, the 10, and the 11. Oh God, takes a long time. Again, I'm forgetting about this. Now I shall not forget. I think 11 should go to the 12, 13, 14, and I think we still have the register 15. I'm not sure, but I'm going to... I'll just do it until 14. I think this is good enough for demonstration purposes. 12, 13, 14. Should look good. Now what I want to do at the end is actually have the stack pointer and the instruction pointer. So those are 2 important ones that I definitely want to show. No comma. This time I don't forget. Let's put here the stack pointer and the instruction pointer, and nothing more. Okay. Looks good. If you remember, our breakpoint was at F0, and here we have F1. This is because we inserted the trace, the CC in hexadecimal. So this instruction was executed, and it's 1 byte long, so we are not at the correct position. We can just fake by adding the minus. This is pretend that this is correct, which is not really. And when we print the registers, we say here you need to subtract 1. Okay, and now you see that it's the same value. Good. Now what we need to do is we need to, or actually, let's So let's remove this value here, and let's do the following. Instead of doing this one, it's probably a little bit better now that I think about it. We just print this one, we don't fake anything, but here we are going to do the trick. So we need to pass this value. Here we need the register RIP to subtract 1 on this register. Because now we can set the registers, so at this point we can definitely, instead we had the issue that we needed this address to continue, and this address was 1 point forward. So we write the origin, we set the registers, so should be the set regs. Let me see if this is matching. So set regs, yes, the request, it loads from the structure reg provided by the address. Okay, so we are fine here. This is ignored. We set the registers. And what we need to do then, we need to do a single step. I think step, set step, clear step. Let's look from the beginning. Yep. Single stepped instruction, address should be passed 1, and we have a signal. We don't need a signal, so we copy this one. So we do step on the PID. Here we don't need this, we pass number, okay, should be fine. And then we are going to write back the trap after we step. No, the trap, not step. But after the step we need actually to wait for the process. I think this should be okay. And then we write this and then we can continue. Okay, let's try this. Looks okay. The thing here is that again it didn't print anything because it's doing several iterations, but if we put 1 it should do it. Let's see. So we are at this point. Set the registers. Actually, I am doing quite a lot of ptrace here, so let me just, just to make sure that everything is fine, if this is less than 0, error pt get regs, here print register, if this one also is less than 0, error pt set regs, if this is less than 0, error pt step. I don't expect this to have any, okay, the continue. I see one possible issue because we set the trap and then this is a little bit dumb because the continue, I see already. So it was not an issue of errors. We had seen here that we need to write a number 1 to indicate is to pick up the execution at the point where it left off. So we don't write this one here, but since we did already such great things, and then just let's do it. If this is less than 0, error pt continue. Let's try it again with the number 1. Yep, we see here number 1, number 2. So another interruption. Okay, where were we? Let's see. Compile. Here factorial 1, and with 3 it doesn't go further. Or does it go further? No, it doesn't go further. So let's do one thing. For the time being, we can just remove the here. And we can just circle back. We can just put here some again loop. And where we have the continue, we can just say go to again. Let's try to see. Okay, now we can see the factorial is here correct. And let's see, we can also add here after the print registers, we can also add a get char. So let's do this. So we get the first iteration, second, third, and yes. So let's see, let's do the factorial of 4. And let's have a look here at test.c. So this function here gets one argument, which is an integer n. This integer n typically in the assembly code, it's passed on the register RDI. And what we can observe here is, since I asked for the factorial of 4, we have the parameter because we set the breakpoint exactly at this function, and we see that n is equal to 4. Then we call the function recursively with factorial of 4 minus 1, which is 3. So we would expect to see here the number 3. There we go. Then we call it with number 2. Okay, number 1. And now it stopped here, and it says, okay, if it is 1, yes, it is, then we don't do any other iteration. We say the result is 1, return everything, and we should get the factorial is 24. Awesome. So here we have a small debugger, a very small debugger written in C, which just takes one address and just it demonstrates the principle of a debugger. To make it more complex, we could add additional breakpoints. We could add loading from ELF symbols from the file, so that instead of giving the memory address, that we say, okay, we want to stop at the factorial. So we would need to search for that one. But that would be for another video. This is becoming already way too long. So thank you. If you followed the video until now, thank you for watching. If you have any questions or comments, please leave some comments down below. Otherwise, thank you for watching, and I wish you have a nice day. Take care. Bye-bye.